Hi everyone, so we're going to continue on with the example that we left off with yesterday. Again, we were still doing some examples thinking about the different types of forces that are acting in a system that are doing work on the system. And specifically, we're thinking about also non-conservative forces as well as conservative forces. So this would be like the biggest type of problem that you could have in terms of energy, because we have to think about all of the different types of forces that could do work, whether they're non-conservative like friction, or if maybe they're more of a conservative force like gravity. Okay, so we did part A together in the last one, and we should have got our speed there to be 2.54 meters per second. So let's do this part. And remember, let's just go back and think that we had this crate, and this crate was going to slide down the ramp, and the ramp has a length of 1 meter. It is 0.5 meters above the ground, and it's at a 30-degree angle. And in that first part, we just wanted to find that final speed of that crate as it hits the bottom of the ramp. So in this question, it says, how far does the crate slide on the horizontal floor if it continues to experience a friction force of magnitude of 5 newtons? So the crate has reached the bottom of the ramp, and now it's just sliding on that horizontal floor now. So let's get an idea of all of the forces that can be acting here, or what work we'll have done on this. So ultimately my goal is, let's go back, how far does the crate slide on the floor? So I want to know a displacement. I want to know a distance here. So we want to find, oh no. We're trying to find delta x. Which I realize you guys can't see that at all in your screen. We're trying to find delta x. I'm trying to find that change in, specifically in my distance here, that crate is going to slide along the floor. Now, if my crate now is sliding along this horizontal floor, so it exited here off of that ramp, and it's moving this way, where is ultimately that going to stop? So what is this distance here? Or we have actually called that delta x here. We found in part A the speed of that crate as it hit the bottom of that ramp. So it's on the floor now. And that speed was 2.54 meters per second. So now looking at this problem, that's going to be this initial velocity here, starting off when the crate is on the floor as it's moving across that horizontal surface. So we know that the initial speed here now of my crate is 2.54. And ultimately, friction force will work on it so much that it's going to come to a stop, because we want to know how far is it going to move when it's acting with friction. So I know then that the final speed must be 0, because that block is going to come to rest. Okay, and let's think about, in part A, we said that this was an isolated system because I can think about the crate and the ramp and Earth being one giant system. Well, let's do the same thing here. Let's say that the crate interacting with the surface and the Earth is just one system. So if I can say that this is an isolated system, which we are, I know that the change in mechanical energy is equal to 0. And remember that the change in mechanical energy is simply this change in my kinetic energy plus the change in all of my potential energies, and that all equals 0. We don't have to worry about a spring constant here, so we're not dealing with elastic potential energy because we don't have a spring. If I'm thinking about my gravitational potential energy, let's say that would be delta U sub G. Since this box isn't moving up in this problem any height, then technically I know that that is mg times my change in height. And since my change in height is 0, all of this is just equal to 0. But I'm missing one thing, because they told us in here that we also have friction. So I need to rewrite this as delta K plus my non-conservative force friction, which we call delta E INT. That's my internal energy, my change in internal energy. All of that is going to be equal to 0. Okay, so let's think about our delta K. We know, I'm going to actually make this smaller, guys. Okay. We know that our delta K plus our delta E sub INT equals 0. So we know delta K is 1/2 mv final squared minus 1/2 mv initial squared. Well, we just said that our final speed, because remember that block is going to come to rest, so that final speed is 0, which means that this whole thing is now 0, so I don't have to worry about that at all. My initial speed we found to be 2.54, so right now I have negative 1/2 times the mass of this block, which was 3 kilograms, times my 2.54 meters per second, that's squared. And then remember, our delta E, our change in internal energy, is just that frictional force times the displacement. And remember, we're trying to find displacement. I'm trying to figure out how far of a distance is this crate going to be moving. Well, they told us in the problem that our friction force is going to maintain that 5 newtons. So we're going to say plus 5 newtons times D. All of that equals 0. So if I do my math here and simplify this, since this is a negative, I'll add it over here to this side. If I then divide by 5, we should get our displacement to be 1.94 meters. So that should be our answer then for B. Okay, so let's do another example problem. Okay, so another problem if we're thinking about, now let's have a spring involved as well. So this says without friction, the energy is going to continue to be transformed between kinetic and elastic potential energy. So the total energy is going to remain the same. So let's say that I have, because we're not changing in height, so we don't have any gravitational potential energy. So this block is going to compress the spring. The spring force is going to push it back out to reach its equilibrium position. And then once it does that, the block will then leave. So we can see that here. The spring will push it out, the block will leave, changing all of that elastic potential energy into kinetic energy. And that's only if we're thinking about it as that crate is moving on a frictionless surface towards the spring. But let's say that friction is present when we have an example with a block or a mass moving into a spring. So if friction is present, then we say that the energy will end up, this total energy will end up decreasing because we're losing some of that energy in the, because of friction. So my delta, my change in mechanical energy, remember my change in mechanical energy is just the sum of the kinetic energy plus the sum of all of the potential energies. So all of that is equal to a negative Fk, which is just my force of friction, times the displacement. So if we have friction present, then that's what we're going to have to use here. So let's do this example. It says that a block having a mass of 0.80 kilograms is given an initial velocity of 1.2 meters per second. So this just says VA. So the block right here is moving with an initial speed of 1.2 meters per second. And it's moving to the right. Ultimately, it's going to collide with this spring, and it's going to compress that spring. And we'll say the spring has negligible mass. The spring also has a force constant of 50 Newton per meters. And let's assume that the surface is going to be frictionless. I want us to calculate the maximum compression of the spring after this block collides with the spring. So after that block is now converting its kinetic energy into some elastic potential energy here, I want to know what's that maximum compression that block is going to cause. And again, we're assuming no friction right now. Okay, so since we don't have a change in height, we don't have, I know, again, you can't see that. So since we don't have a change in height, we don't have this. This is just going to be equal to 0. So our potential energy based on gravity is just 0. We will have some type of kinetic energy, and we know we're going to have some type of change in elastic potential energy. So I'm going to have something here, don't know what it is, going to have something here, and since this is frictionless, and I know that I can set my system to be the spring interacting with, I can set my system as the spring and the block. And if I think about my system as that, there's nothing else acting on those things. So then we can say this is an isolated system. So then, like we've said, our isolated system is my change in mechanical energy equals 0. We know our change in mechanical energy is the sum of the kinetic energies plus all of the potential energy. So we don't have our gravitational potential energy just because we're not moving up that height. I don't have a vertical displacement. We will have some type of kinetic, so I need to write my delta K. And I will have some type of change in elastic energy, elastic potential energy, so plus delta US, all of that should equal 0. Okay, well we know that delta K is 1/2 mv final squared minus 1/2 mv initial squared. So that's all of that. And then if I'm thinking about the change in potential energy of the spring, then we know that that's our 1/2 kx squared, and that would be that final position. And then that's minus my 1/2 kx, that initial position of the spring, and that's squared. Okay, well let's see if we can simplify any of these things down. Maybe some equal to 0, and then let's also plug in our numbers. Okay, so our final speed. So the block is moving along and it's compressing the spring, and at maximum compression, that means that that block is going to be at rest. So the final velocity here is just going to be equal to 0. So that means this piece can be gone. So that would leave me with a negative 1/2. The mass of the block was 0.8. So we can have that. And then they gave us an initial speed of 1.2 meters per second. We're going to square that. Okay, and then let's add that to what we have here. Again, I'm trying to find the maximum compression of this spring. So I'm trying to find, actually, this XF. I want to know, ultimately, how much that spring was compressed. And I know that initially, that spring was at its equilibrium position. So its initial position, x sub I, is equal to 0. And if that's equal to 0, all of this must be equal to 0. So now that's gone. So I'm going to have part then of my kinetic energy here plus the 1/2. They gave us that K constant, I think that was 50. Yeah, 50 Newton per meters. And times x sub F squared. And that x sub F is what we're trying to find. And all of that equals 0 because we said this is an isolated system. Okay, so multiply and then add over here to this side, and then if I divide that by 25 and square root, we should get our final position, or that maximum compression, to be 0.15 meters. All right, guys, let's look at the next problem. And the next problem is dealing with those energy... Oh, nope, just kidding. We have one more to do, guys. Actually, will you, because tomorrow in class we're going to be talking more about Chapter 8. So will you tomorrow in class... will you do this problem for me, and I want you to try it for, I want you to try this problem tonight for homework, please. and then we'll look at them together to see what we get for, ultimately you're going to be writing a formula that's representing the coefficient of kinetic friction. So I want you to try this one together. I want you to try this one tonight at home, bring it tomorrow for class, and we'll look at them. This problem is just showing us, just being able to interpret an energy bar graph or an energy bar diagram is pretty important. So we have the energy bar chart is showing 3 instants in the motion of the system, and that's described here. We have all of our different ones, and ultimately we're doing this for that last problem here. I have a mass that's attached to a spring, and then I also have this mass is attached to another mass that's over a pulley. So we have like an Atwood's machine that then is also attached to a spring, and know how much we love our Atwood's machines. This spring is compressed, so it's going to reach out back to its equilibrium position, and it will start to stretch out, possibly past its equilibrium position. That mass is then going to move at some specific height. So all we did was show these as energy bar diagrams. So actually, I'll come back to this one too whenever we talk about the last problem in class tomorrow. So hold off on this one. I want you to try the last problem though on your own. We'll do that one at the beginning of class, and then we'll also talk about this one after we've done that. Guys, the last thing that we need to talk about is power. And ultimately power is just the time rate of energy transfer. So power is really easy. I think about power as, we can think about power as just the work being done in terms of that energy transfer method over time. So instantaneous power is just my dE over dt. It is a rate. So it's the time rate of energy transfer. If we think about it in terms of work, if we're talking about like the average power that we have, we can say that it's equivalent to work over that change in time. Okay, so continuing on with our instantaneous power, the instantaneous power is the limiting value of the average power, and that happens as the time approaches 0. Guys, ultimately on this, I can say that power is also equivalent to my force times then V, then my speed, or my velocity. Sorry, because it's a vector, so velocity. So power can also be written by thinking about it as my force times my velocity. This is valid, this term of power being my force times my velocity. It's valid for any energy transfer. So if we think about whether or not it is a scalar or if it's a vector, power is definitely going to be, I'll let you decide and you can tell me tomorrow. The unit of power is called a watt, and 1 watt is equal to 1 joule per second. So if we simplify that down even more, just like we need to know a Newton meter is equal to things, we need to know that a joule per second is going to be equal to this. Kilogram meter squared over seconds cubed. A unit of power that we use in the United States is something called horsepower, and we in science use watts, but here in the United States we use horsepower, and 1 horsepower is equal to 746 watts, and that's something that we'll just need to know. We can also express our power in terms also of units of work or energy. We can think about it in joules. We can have a kilowatt hour, and I'm just having my I just have my 1,000 watts, and if I multiply that by a time, I'm going to end up with joules. So units of power can also be expressed in terms of joules as well. Guys, this is the last slide that we have. The last 2 slides are just summaries of what we've been doing. We're going to do this one together in class tomorrow as well. So I want you to try the one problem with the Atwood's machine with the spring, and then